We try to look into problems on mathematical induction from the book Elements of Number Theory by David M. Burton. So we'll try to look into all the questions and try to solve the problems on mathematical induction from that book. So let's start off with the first question, which is 1 into 2 plus 2 into 3 plus 3 into 4 all the way n plus 1 should be equal to n plus 1 n plus 2 whole thing divided by 3. This is what I am required to prove using mathematical induction. So the first step is the base case. So let's check with the base case n equal to 1. When n is equal to 1, so this becomes 1 into 1 plus 2. So this is 1 into 1 plus 1 is 2. So 1 into 2, this is what I am having in the left hand side. What about the right hand side? Right hand side I am having 1, 1 plus 1 and 1 plus 2 whole thing divided by 3. So 3 cancel, it's 2 into 1 is 2 and this one is 2 as well. So left hand side is equal to right hand side, so the base case is true. Then we will assume by induction that the statement holds true for n equal to n. And next we will try to check whether the statement holds true for n equal to n plus 1. So for n equal to n, we are assuming this is true. So using induction hypothesis, I claim that 1 into 2 plus 2 into 3 plus 3 into 4 plus all the way and n plus 1 is equal to n plus 1 n plus 2 divided by 3. This I am claiming to be true using induction hypothesis. I need to prove now that the statement must be true for n equal to n plus 1. So if I am replacing this with n plus 1, so the equation will change into this will remain as it is, and the next element is going to be n plus 1 and the n plus 1 plus 1, which is n plus 2, and that should be equal to n plus 1, n plus 1 plus 1, which is n plus 2, and n plus 1 plus 2, which is n plus 3 divided by 3. This is what I am required to prove. So what I have is this one, and what I am required to prove is this one. So maybe I need to take the left hand side. So if I take this part, left hand side, so left hand side, now we can see here from here to here, I have the same thing as it is, and because using induction hypothesis I claim that this portion is equal to n plus 1 into n plus 2 divided by 3, so I can replace the whole thing with this whole part with this number. So left hand side is this, so I'm replacing this whole thing with n plus 1 n plus 2 divided by 3 into n plus 1 and n plus 2. Well, now if I multiply this thing, so yeah, I've got a plus sign here, not multiply, plus sign here. So this would change into a 3 here, and then n plus 1, n plus 2 plus 3, n plus 1 and n plus 2. I can see here that I've got a n plus 1 common, so maybe I can take, or even I got the n plus 2 as common, maybe I can take the n plus 1 and n plus 2 as common. So n plus 1, n plus 2 common. What I am left here is a n, and what I am left here is a 3, and the whole thing is divided by 3. So basically what exactly this is, a n plus 1 and a n plus 2 and a n plus 3 divided by 3, and exactly this is what I am required to prove. So done. So that's how we need to prove this statement. We'll look into the next problem, which is a to the power n minus 1 is equal to a minus 1, a to the power n minus 1 plus a to the power n minus 2 all the way to a plus a 1. We need to prove this statement using induction. And in order for me to prove this statement using induction, I need to look at the base case. So this particular statement is valid for n greater than or equal to 1. So the base case is 1. So a to the power 1 minus 1 is a minus 1. And what do I have here in the right hand side? A minus 1, and here a to the power 1 minus 1 is 0, which is 1. So 1 into this whole thing is also 1, so this basically is a minus 1. So left hand side and right hand side are equal. So that means this particular statement holds true for the base case, which in this case is n equal to 1. What about the next step? So I assume that the statement holds true for n equal to n, and that is induction hypothesis. So I am assuming this particular statement is true using induction hypothesis. And then I need to prove that the statement must hold true for n equal to n plus 1. And if that is the case, so finally what I get is a to the power n plus 1 minus 1 is equal to a minus 1, and here a with the n replaced with the n plus 1, so this becomes a n plus this becomes a n minus 1 plus a plus 1. This finally is what we are required to prove. So this is to prove, and this is what we are having using induction hypothesis. So to prove this statement, probably one of the approach that we can do is go reverse. So if finally I am required to prove this statement that a to the power n plus 1 minus 1, if finally I am required to have that something, whatever I am assuming, that should turn out to be equal to this one. Finally, that means the step prior to this one definitely is this step. So maybe I will write down this step, which is a minus 1 with the a to the power n plus a to the power n minus 1 plus all the way a plus 1. So this is my final step, and this is the step prior to my final step. So somehow this was manipulated using this. So maybe I try to write down this statement based on this. So if that is the case, what I should have done is probably the step prior to this one would be a minus 1, and then I will have a common, and then a n minus 1 plus a n minus 2 plus all the way plus a 1, because this a will become 1, and then I will be left with the extra 1. So this is what I am having. Now since I am having this extra 1, I somehow need to fit this extra 1 in this form. And in order for me to fit this extra 1 in this form, what I can do is I can add up this extra bit. And if I am adding up this extra bit, in that case I also need to subtract that extra bit to keep it as it is. So that means this particular step will be a to the power n minus 1 plus a n minus 2 plus a 1, and then I'm adding up this whole thing, a to the power n minus 1 plus a to the power n minus 2 plus a 1. So all this extra bit, whichever I added up, in order to make this into this form, I need to subtract that to keep it as it is. So I'm subtracting the same thing again, all the way up to here. I got this extra 1, so that definitely that means I'm not going to add up this extra, subtract that extra 1, because this is the actual extra part that I was having. So I added up this bit, so I need to subtract this bit. That means I need to subtract it a. So this is what I am having. So if this is the case, so that means the step prior to this step would be, because again here I need to write down this into exactly this form, and in order for me to do so, what I need to do is probably here I can take the a, and if I take the a common, so I can take a common, and in that case this would become a n minus 2, this becomes a n minus 2, and this becomes a 1. So this is what will end up. Now if this is what I should have got, so quite clearly I can see here I have got this portion and this portion which is common. So maybe I can take out this common factor, and then if I am taking out this common factor, which is a to the power n minus 1 plus a to the power n minus 2 plus all the way till 1, what the extra thing I am having is, here I have a plus 1, because here I have got a and here I have got a 1. I took this and this common, so I have got a plus 1, and then also I have got a minus 1. And also I have for this one, because the whole thing is multiplied by a minus 1, so that means even with this also I have got a minus 1, so minus a with a minus 1, and that's this whole thing, a to the power n minus 2 plus a to the power n minus 3 all the way till 1. Now we can somehow make some sense, because I know a to the power n minus 1 is equal to this value, and here I have this whole thing with a minus 1. So this and this being multiplied together is actually, this and this are multiplied together, so this actually is a to the power n minus 1. So that means this whole thing I can now replace with a to the power n minus 1, which is multiplied with a plus 1, and this one. What about this one? Here I have got a minus a, and then a minus 1 multiplied with a to the power n minus 2 plus a n minus 3 all the way till 1. Now if you look into this one and if you look into this one, so this basically is, this whole thing is actually a to the power n minus 1 minus 1. So I can replace this whole thing, I can replace this whole thing with a minus a, and this whole thing is a to the power n minus 1 minus a 1. So what should have been the step prior to this one? So the step prior to this one definitely would have been some multiplication of this and this. So this would be a to the power n plus 1 multiplication normal, and plus a to the power n, a minus of a, and then a minus 1, and the minus of this going to be a to the power n, and this is going to be a plus a. So you can see here, this is a plus a to the power n minus a to the power n minus a plus a minus 1. So this is, this and this would cancel, this and this would cancel. What I should have is a to the power n plus 1 minus a 1. So what we are required to prove this statement, and we went from the final step and went to the first step. So this is what I am required to prove. The step prior to this one is this one, so that means I should have started off here, and then the next step would have been this one, followed by this step, followed by this step, followed by this step, this, and then we are done. So this is another approach where we can start things from the end, and then we can move backward and come to the beginning portion. Why this is essential? Because normally if we do problems, probably the thing might not start to us that this we must manipulate in terms of a to the power, I need to add up a to the power n, subtract a to the power n, add a minus a. So this thing might not have stuck in our mind. We came to know this by moving backwards. So sometimes in certain cases, while we do try to prove a problem using induction, it is advisable to start moving start from the end and start going to the portion that you should have actually started off your answer. So started from the end and went up to the beginning. So this is one of the approach that can be used to solve problems in mathematical induction. Well, so we need to follow different techniques in order to solve problems involving mathematical induction. Maybe we now try to look into another problem, and the problem says cube of any integer. When I write it completely, can be written as the difference of two cubes. We need to prove this statement using mathematical induction. What the problem says, cube of any integer can be written as the difference of two cubes. Sorry, of difference of two squares. It should not be cube, squares. Sorry. So, before we proceed this, maybe we try to see some example and have a feeling for what exactly the question says. Cube of any integer. Let's say I'm taking one cube. One cube is 1, and 1 is 1 square, and 1 square, it says cube of any integer can be written as the difference of 2 square. So basically n cube can be written as a difference of 2 square. So 1 cube, can it be written as difference of 2 square? Well, quite natural, it can be written as 1 square minus 0 square. What else we can have? Let's try to see 2 cube. What about the 2 cube? 2 cube is 8. Now, can 8 be written as the difference of 2 square? Well, 2 cube is 8, and 8 is a 9 minus 1, which basically is 3 square minus 1 square. Well, it can also be written. So that means this statement holds true for n equal to 1, 2, and in general. So if this is the base case, well, the statement holds true for the best case. So to have a more feeling about this question, let's try to see how the sum of the cube would look like. So if I'm taking a 1 cube plus a 2 cube plus a 3 cube all the way till n cube, we know this is equal to n plus 1 by 2 square. This is normal high school mathematics. Well, this I know. If this is the case, so maybe I try to check what about, because the number prior to n was n minus 1 cube, so maybe now I try to see how much is this square, the sum of this one. So sum of the number from 1 cube, 2 cube, 3 cube all the way to n minus 1 whole cube is going to be, I need to replace this n with n minus 1, so this becomes a n minus 1 and this becomes an n with a 2 square. So in other words, I can say, so n cube is equal to sum of all the number from 1 till n minus sum of all the number from 1 till n minus 1. This is going to be the value of n cube, and quite natural. I can see here this does make sense because I quite clearly I can see the difference in these two, because this one, the sum is from 1 to n cube, and this sum is from 1 to n minus 1 whole cube, and so that means the difference between these two is actually a n cube, and this n cube, that means basically is this minus this. So it is n plus 1 by 2 whole square minus say n minus 1 with the n by 2 whole square. This is exactly what we have, and it makes sense. So that means this statement is definitely correct. So before we could proceed this problem, the thing that we should keep in mind is to get the equation, because here we do not have any equation. So in order for us to get the equation, what we should do is we need to write down all the cubic summation up to n cube, which is n plus 1 by 2 and then whole square, and then I need to write down the summation till n minus 1 whole cube, which is n minus 1 with the n by 2 whole square, and then if I subtract this two, if I subtract this from this, I end up getting an n cube, which turns out to be equal to n plus 1 by 2 whole square minus a n minus 1 with the n by 2 whole square. So this is what the statement says. So any cube can be represented as the difference of 2 square, what we have seen here so far. And I need to prove that the statement holds true for n equal to n plus 1 as well. So I need to replace this n with n plus 1. So if I am replacing this n with n plus 1, what this will become? This will become a n plus 1 whole cube, and this is going to be a n plus 1 with a n plus 2 by 2 square minus this is going to be a n, and this is going to be a n plus 1 divided by 2 whole square. Ultimately, this is what I am required to prove, and to prove it, this is what I have, and this what I have is the induction hypothesis, and this I managed to get using this fact. So this equation was not given. So the good thing is, sometimes you might not be given the equation and you need to frame the equation, and in order for you to frame the equation, you should have the background knowledge, and in this case, this is the background knowledge that you require in order to get this equation. So once you get this equation, so from here to here we need to prove. Well, how can we prove this? Maybe what we do is take the right hand side. I can also take the left hand side, but if I take the left hand side, it's going to be more lengthy. So if I take the right hand side, in that case, it's going to be a bit easier. How it's going to be easier, we'll surely find it out. So maybe we just check into this portion and try to get this from this one. Well, so I'm taking the right hand side, which is say n plus 1. I'm taking right hand side for this one, the one that I'm required to prove. N plus 1 with the n plus 2 by 2 whole square minus a n with the n plus 1 by 2 and again a whole square. Well, what I clearly can see is here I have got a n plus 1, here I have got a n plus 1 square with the n plus 1 square with the n plus 1, a 2 square. So maybe the best option for me it would be to take the common factor. So I'm taking the common factor out, so it's going to be n plus 1 whole square by 4, and what I am left over is a n plus 2 whole square minus a n square. Remember, it's an n square. Well, this is going to be an n plus 1 square divided by 4, and this is going to be, now I need to break it down, n plus 1, n plus 2 whole square is going to be a n square with a 4 plus a 4n minus a n square, and I've got this n squares cancel out, and then what I am left is this portion. So this is going to be a n plus 1 whole square by 4, and this I'm taking the 4 out, and this is going to be a 1 plus n, and then this 4 and this 4 cancel, and I've got 1 plus n whole square with a 1 plus n, so it's going to be a 1 plus n whole cube, and exactly this is what I'm required to prove, QED. So that's how we can prove this statement. Okay, next try to see few more examples, not examples, all these are the problems given in that book. It's very much essential for anyone whoever is preparing for mathematics Olympiad. Very much essential. One of the fundamental book that you need to study, and you need to completely go through this book in order for you to prepare for Olympiad, International Mathematics Olympiad. Let's try now to look into this equation, or we try to solve n factorial is greater than n square for n greater than equal to 4. We need to prove this statement using induction. So how can we prove this statement? So before we prove this statement, again let's try to check out the mind of the guy who prepared this question, how probably he came up with this question, like, you know, for this equation to be valid, the n should be greater than equal to 4, how probably he might have thought of. Well, n factorial greater than n square. N factorial I know is n with the n plus 1, sorry, n minus 1 factorial, which is greater than n squared. So here n squared, here I've got n, so basically this is n minus 1 factorial greater than n. Well, so this is a n minus 1 with the n minus 2 factorial greater than n. Well, this is n minus 2 factorial greater than n minus 1. And then, now, if I divide, so this is the factorial, so if I divide n if I divide n by n minus 1, I won't divide, I will just write down the value. So the value, I somewhere wrote it, I don't know where I write it properly, I need to do the division itself. No, I have, in fact, with me. So if you divide this, what we end up getting, n divided by n minus 1, it turns out to be this value is actually 1 plus 1 by n plus a 1 by n squared plus a 1 by n cubed, and so on. So that means what exactly I have is n minus 2 factorial is greater than 1 plus 1 by n plus 1 by n squared plus 1 by n cubed plus dot. And so basically this is the statement, and from here we'll try to see when this equation makes sense, is valid. So the moment n is equal to 1, so 1 minus 2 factorial not valid, n equal to 2, 2 minus 2 factorial is 0 factorial, which is 1, and here it is all definitely greater than 1. So if I put 3 minus 2 is 1 factorial, which is 1, and here 1 plus something, so definitely again does not make sense. Now when n is equal to 4, so this becomes a 2 factorial. If n is 4, this becomes 2 factorial. 2 factorial is 2, and if n becomes 4, so then this becomes a 1 plus a 1 by 4 plus a 1 by 8 and so on. And I know this value is equal to a half and this is 1. This value is approaching towards half and this is a 1. So this is roughly 1.5. Definitely 1.5 is lesser than 2, and that is why n greater than 4. That's how this question was framed. Okay, so now we are going to see how to solve this problem using mathematical induction. I am required to prove that n plus n factorial is greater than n square for n greater than equal to 2. And in order for me to prove this statement, let's try to check using induction hypothesis. So with n equal to 2, my left hand side becomes 2 factorial, which is 2, and right hand side becomes a 2 square, which is 4. Sorry, the question was not 2, it was 4, correct? Oh, sorry, for n greater than 4. So this, if I'm replacing this n with a 4, so I've got a 4 factorial here, so left hand side is 4 factorial, which is 4 into 3 into 2 into 1, which turns out to be 3 4 12, 12 24. And what about here? So a 4 square, which is 16, and 24 is greater than 16, so that means this statement holds true for n equal to 4. So that is my base case. So next I'm assuming by induction that this statement holds true for n equal to n. So that means I'm assuming this is true. So this is, I'm assuming using induction hypothesis, this is true. What I need to prove that this statement must hold true for n equal to n plus 1. So now I need to replace this n with n plus 1. So this becomes a n plus 1 factorial, which is greater than n plus 1 square. So how can I get this form from this one? Because I have this one, so quite natural, since I have n factorial already greater than n square, and to get this form it is quite easy, because if I multiply n plus 1 both sides, it becomes a n plus 1 factorial greater than n square n plus 1, and if this is the case, this becomes actually a n cube with a n square. So I can write down this as a n cube with a n square. So this is what I have, and this is what I am required to prove. This is what I am required to prove. Maybe next thing what I can do is break down this n plus 1 whole square into, I can definitely break it down into a n square plus a 1 plus 2n. So this is what I am required to prove, and this is what I have. So I have this one, and then if somehow I can prove that this is bigger than n square plus 1 plus 2n, then I am done. So how can I prove this statement? So I need to prove indirectly. What I need to prove is n cube plus a n squared is greater than n squared plus a 1 plus a 2n. I need to prove this. And in order for me to prove this, what I can do? So here comes a twist, another way of looking into a different way of solving problem using some sort of clever argument, a different approach to solve problems on mathematical induction. So I'm not going to use this fact anymore. Rather, since I have a n greater than 4, it's given, so this also implies that n definitely is greater than 2. If this is the case, so from here I can say, well, n square is greater than 2n, multiplying n both sides. And this also implies, say, n square greater than 2n plus 1. So this is my first statement. Now, again, if n greater than 2, since n is greater than 4, this was given, and based on this, because n greater than 4, that also implies n should be greater than 2, and it also implies that n should be greater than 1. If n should be greater than 1, so this, now what I can do is maybe I multiply square both sides. So if I multiply square both sides, so this becomes a n cube greater than n squared. This is number 2. Now if I add these two up, I end up getting a n squared plus a n cube. I am adding up 1 and 2, so n squared plus a n cube is greater than 2n plus 1 plus a n squared, or this exactly what I am required to prove, QED. So this is another way of solving problem in mathematical induction, where we need to not directly take this value, but what I did is use this particular condition. Since it is given that n is greater than or equal to 4, so what I did is, because n already greater than 4, so definitely n should be greater than 2 as well, and n should be greater than 1 as well. And by doing so, I manipulated the square and the cube term. And by doing so, as you can see, I arrived at the solution. So this is another way of solving problem in mathematical induction. So the same type of argument, let's try to prove the fact that here now what we have proved so far is n factorial greater than equal to n squared. Now maybe I will try to prove the n factorial greater than n cube for n greater than equal to 6. If I am required to prove this statement, again we are going to use the same approach, nothing different. So n greater than equal to 6, this particular statement must hold true. So 6 factorial base case is greater than 6 cube, correct. Next, I am trying to prove this, or rather using induction hypothesis, I am assuming this particular statement hold true. So this is true. So this statement is true, and I am claiming this statement to be true using induction hypothesis. Now I need to prove that this statement also hold true for n equal to n plus 1. So this would become a n plus 1 factorial greater than a n plus 1 cube. This is what I am required to prove, and this is what we have. So this is what we have, and this is what we need to prove. So how can I get this from this one? So again, using the same approach, that I can multiply n plus 1 both sides. So I'm taking this fact that n factorial greater than n cube, this using induction hypothesis, and then I'm multiplying n plus 1 both sides. So this would become an n factorial with the n plus 1 greater than a n cube with the n plus 1 being multiplied. So this becomes a n plus 1 factorial greater than n cube n plus 1. So this becomes n to the power 4 plus this becomes a n cube. So this is what we are to prove, and this is what this is what is given, what we have, and this is what we are required to prove. Again, we'll be using the same technique, break it down into, so I know n plus 1 whole cube is basically a n cube plus a 1 plus 3n n plus 1. So if we can prove that n to the power 4 plus n cube greater than n cube plus 3n n plus 1 plus a 1, we are done. So how can I prove this statement? Again, we'll be using the same approach. Given n greater than equal to 6. So here I have got a 3. So maybe I would say, well, n greater also implies n greater than 3. Now, maybe again I will do the same thing n square greater than 3n. Again, we know n square should be greater than a n plus 1, because n is always greater than equal to 6, and so n square, so here I've got a n with the n, and this one is n plus just a 1, so definitely this is going to be greater than this value. And if that is the case, oh, in certain case, because if I put n equal to 1, and I put n equal to 1, so this one basically I need to give it this way, n square greater than equal to n plus 1. And now if I multiply this two, so this becomes a n to the power 4 greater than equal to greater than 3n n plus 1. Or similarly I can say, well, n to the power 4 is greater than equal to 3n n plus 1 plus a 1. Again we have, since n was greater than equal to 6, so naturally n also is greater than 1. Here I got a n cube, so I can say, well, n cube is I'm squaring it, and I can, or maybe what I can do is, since I have got this value, so even I don't need to do all this thing, so from here what I can do, I can add up the n cube both sides, so this becomes n to the power 4 plus a n cube, which is greater than equal to 3n n plus 1 plus a 1 plus a n cube. So done, Q18. So what did I do here? Again, the same approach. I'm given this statement, I'm required to prove that the statement holds true for n plus 1. So I multiply this with n plus 1, I end up getting this thing. And so this is what I got, and this is what I am required to prove. Now what is the difference between this and this? So here I got a cube, here I got a cube, and here all this thing, and here I got a n to the power 4. So this whole thing should be greater than 1 to the power 4. If I manage to prove it, so then we are done. So in order for me to prove n to the power 4 greater than this thing, what exactly I used? Again, the fact that since it was given n greater than equal to 6, so I assume if n is greater than equal to 6, quite natural, n is greater than will be greater than 3. And why specifically 3? Because I have got a 3 here, so n greater than 3. So then I made it a square with a 3n in order to get this form. And then using the same fact that each n greater than n square greater than n also implies that the n definitely is going to be greater than equal to n, very natural, or a n square should be greater than equal to a n plus a 1. Because what I mean to say is n equal to n, and I'm squaring it. So if I'm squaring it and then I'm adding 1 here, so this should be the case. So this, and then I multiplied this with this, I ended up getting this term. And then since I need to just add a n cube both these sides, so I added up n cube both these sides, and I ended up getting what I am supposed to get. So done. Next, we'll try to look into other problems, and this problem is a bit interesting. The result is interesting because we need to use this particular result, whatever we'll be doing now, in a lot of other cases. We'll be using that result to prove few other problems as well. So what the statement says, we need to prove 2 into 6 into 10 all the way to 4n minus 1, that should be equal to 2n factorial divided by n factorial for n greater than equal to 1. I need to prove this statement using induction hypothesis. Sorry, using mathematical induction. Well, how can I prove this thing? Well, for n equal to 1, so this becomes a 2 into 1 factorial divided by a 1 factorial. So basically this is 2 divided by 1, which is 2. What about this? I have got only 2. So 2 here, there. So I've got a 2 here and a 2 here. So the statement holds true for n equal to n. Now, sorry, the statement holds true for n equal to, for the base case n equal to 1. Now, using induction hypothesis, I claim that this particular statement holds true. So, I am assuming this to be true using induction hypothesis. And then, I need to prove that the statement also holds true for n equal to n plus 1. So, so exactly what I need to prove, I need to prove 2 into 6 into 10 all the way for n minus 1. What will be the next digit? It's going to be 4 n plus 1 minus a 1, and that should be equal to 2n plus 1 with the n plus 1 factorial, the factorial here as well. So this is what I'm required to prove. Or this statement, or this particular term, 2 into 6 into 10 for n minus 1, this is 4n plus 4 minus a 3. So basically this is 4n plus a 3 should be equal to 2n plus 1. So this is 2n plus 1 factorial divided by n plus 1 factorial. So this is what we are required to prove. Sorry, it's not minus 1, it's 2. So this becomes 4n minus 2, and this becomes 4n plus 4 minus 2, it's become 4n plus 2. So this is what I am required to prove. And in order for me to prove this, I need to prove this statement using this given fact. So straight away I know this whole thing is equal to 2n factorial by n factorial, so I can straight away replace this with this value, 2n factorial divided by n factorial multiplied by 4n plus 2. So what exactly is this value? So this is a 2n factorial, and then here I got 4n plus 2, so maybe I can take the 2 common, so this becomes a 2n plus 1, and then the whole thing is divisible by n factorial. Okay, so next what we can do, so you can see here what I am required to prove is 2n plus 1 divided by n plus 1, so and here I have got an n factorial, so maybe what I need to do is multiply a n plus 1 here, and then in order to keep it same, put it keep 1 plus n plus 1 in the upstairs as well. And the moment I am doing it, so what we can see is, maybe I need to rub this portion. So what I need to do is, quite clearly you can see I've got a 2 multiplied by this one, so this becomes a 2n factorial, and then I've got a 2n plus 1 with a 2 being multiplied by this one becomes 2n plus 2, and the whole thing is divisible by n plus 1 factorial now. And wait, this is 2n plus 1, 2n plus 2, and the 2n. So basically this is 2n plus 2 factorial divisible by n plus 1 factorial, and exactly that's what I am required to prove. QED. So this, what exactly I used, nothing fancy, whatever I have got here, I just kept it as it is. I wrote the next value, converting n into n plus 1, and then for this whole series using induction hypothesis I wrote this value multiplied by what is the n plus next term, n plus 1 term. So whenever I multiplied it, I got this value, but then like what I noticed is the manipulation I did is multiply n plus 1 upstairs and downstairs. What for I multiplied this n plus 1 upstairs and downstairs? Because what I am required to prove has got a n plus 1 factorial in the downstairs. So that means here I somehow need to get a n plus 1 factorial definitely. So that is why I multiplied n plus 1 downstairs. And because I need to keep it as it is, I multiplied that n plus 1 in upstairs as well. And the moment I multiplied it, what I found is I got a 2 here with the n plus 1 being multiplied together becomes a 2n plus 2. And I saw that it's a 2n and the 2n plus 1 and the 2n plus 2. So basically it's a 2n plus 2 factorial. So 2n plus 2 factorial divided by n plus 1 factorial, and that's what I was required to find. So this particular value has got application, and we'll be using that application to solve a problem. And the problem is we need to prove 2 to the power n with the n factorial square less than equal to 2n factorial for n greater than equal to 1. This is what I am required to prove. Now, this I know I can keep one n factorial here, and then I can write this. Why I wrote this? Because just now we found that this value turns out to be 2 into 2 into 6 into 10, and it's 4n minus 2. This is exactly what we found just now. So that means, in other words, I need to prove that 2 to the power n with the n factorial is less than equal to this value. This is what I need to prove. And in order for me to prove this using induction, I am assuming that the statement, so I need to prove it first for the base case, and the base case is going to be again n equal to 1. So if n equal to 1, so this left hand side becomes 2 to the power 1 into the 1 factorial, which turns out to be 2, and here it's going to be 2 as well, and 2 definitely less than equal to 2. This particular statement holds true. So that means this particular statement is true for the base case, which in this case is n equal to 1. Now, using induction hypothesis, I assume that the statement holds true for n equal to n. So this is true using induction hypothesis. Next, I am trying to prove whether the statement holds true for n equal to n plus 1. So I am replacing this with n plus 1. So this becomes 2 to the power n plus 1, and here n plus 1 factorial is less than equal to 2 into 6 into 10 all the way, and here the 4 with the n getting replaced by n plus 1, so that becomes 4n plus 4 minus 2, which is 4n. So this is 4n plus 4 minus 2, which is 4n plus 2. So this is what I am required to prove, and this is what I have. So how do I prove this from this one? Well, let's try to see and look at the left hand side. So maybe I will just look at the left hand side of what I'm supposed to prove, and then somehow try to do some manipulation from what I am being given. So 2 to the power n plus 1 with the n plus 1 factorial. This is my left hand side. Well, this is 2 to the power n into 2 with the n plus 1 and the n factorial. Well, this is 2 to the power n into the n factorial, and then I've got a 2 into n plus 1. I'm writing this separately. I'm breaking it down. So n plus 1 factorial, I break it down into n plus 1 into n factorial, and then 2n n factorial, I'm keeping it one side with the 2 and n plus 1 in the other side. And what for I did is because I want to use this argument. So this is what I have got, 2 to the power n with the n factorial into 2n plus 1 multiplied. So basically this whole thing I can write it down as 2n plus, this whole thing basically is 2n plus 2. So maybe I just need to replace this with a 2n plus 2. What I have here is a 4n minus 2, and here I have got a 4n plus 2. Maybe I need to write down in terms of 4n plus 2. So, and here I have got a, the inequality sign. So maybe I can put the inequality sign and I can write down that 2 to the power n with the n factorial, and here with the 4n plus 2. It makes sense, isn't it? 2n plus 2 definitely is lesser than 4n plus 2. So I'm writing this fact. And this statement up to 4n plus 2 is actually, this whole thing is actually 2 into 6 into 10 all the way to 4n minus 2, and then this is 4n plus 2. I'm replacing this whole thing with this series that we got, and then this 4n plus 2 I'm keeping it as it is. And in doing so, what I managed to get is this statement definitely is less than a 2 with a 6 and a 10 all the way till 4n plus 1 minus 2. So 4n plus 1 minus 2 is 4n plus 4 minus 2. 4n plus 4 minus 2 is 4n plus 2. And so what I did basically, what did I do? So this I just wrote this in this particular form. So this number 4n plus 2 actually is 4n plus 1 minus 2. So in other words, I can replace this whole thing. So I can say, well, this whole thing is lesser than this value, and that's exactly what I am supposed to prove. This statement is less than this value, and we are done. Next, we'll try to prove the famous equation 1 plus a to the power n is greater than or equal to 1 plus an a for n greater than or equal to 1 when rule is inequality. 1 plus a to the power n is greater than or equal to 1 plus na. We are going to prove this using mathematical induction. Well, this statement should hold true for n equal to 1, the base case. So let's try to check the base case. So with n equal to 1, this becomes a 1 plus a to the power 1, and this becomes 1 plus a, and these are equal. So this holds true for the base case. I am assuming that this holds true for n equal to n plus n as well. So I am assuming 1 plus a to the power n is greater than equal to 1 plus na is also true using induction hypothesis. And for the base case, I found that 1 plus a is greater than equal to 1 plus a. So this was my base case. And I need to prove 1 plus a to the power n plus 1 is greater than 1 plus, I need to replace this n with n plus 1, or in other words, I need to prove 1 plus a to the power n plus 1 is greater than equal to 1 plus na plus a. What I have is this one, and what I need to prove is this one. Well, I have got this one, so from here I need to get this one. So this is what I am required to prove from here to here. So how can I proceed from here to here? So very natural, I need to multiply 1 plus a both this side. So if I multiply 1 plus a both this side here, so this becomes 1 plus a to the power n plus 1, and that should be greater than equal to 1 plus na multiplied with the a plus 1. Or in other words, what we get is 1 plus a to the power n plus 1 is greater than 1 multiplied with the a is a plus a 1 plus n into a square is a square into n plus a na. This is what I have, and this is what I need to prove. And very natural that what exactly I have here is a 1 with the a plus a na plus a square n, which definitely is greater than this value, which is 1 plus na plus a. I am required to prove this. I got this value, and this value is greater than this one, so that means this is greater than this. That's what I am required to prove. QED. Next, let's try to prove one more question. Let's try to prove this result. 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus 1 by n square is less than equal to 2 minus 1 by n for n greater than equal to 1. So the base case, n equal to 1. So if n equal to 1, this becomes a 2 minus 1, which is 1, and this becomes a 1. So correct. So the base case is true. I assume that the statement holds true for n equal to n using induction hypothesis, and I need to prove that the statement holds true for n equal to n plus 1. So what I am required to prove, this plus this plus this plus 1 by n squared plus 1 by n plus 1 whole square is less than equal to 2 minus 1 by n plus 1. This is what I am required to prove. So again here, we can go by the normal process, and if we go by the normal process, it will take a lot of time. So the best approach would be go in the reverse way. And if we go in the reverse way, this is what I would get, isn't it? Finally, if I manage to prove it. So if this is what I'm supposed to get finally, so that means this portion I can replace with 2 minus 1 by n plus say 1 plus n whole square is greater than 2 minus 1 by n plus 1. This should be my previous statement. If this should be my previous statement, so I've got a 2 here and a 2 here, so this will cancel. So probably the statement prior to this will be minus 1 by n plus 1 by n plus 1 whole square less than minus 1 by n plus 1. And here I have got a n plus 1 and here I have got a n plus 1. So probably the best approach, the previous step would have been like all the n and n plus 1 in this same side. So if that would have been the case, so the previous step would have been 1 by n plus 1 square plus 1 by n plus 1 less than with the 1 by n coming this side. So if this would have been the case, because here I got a square, here no square, so probably the previous step would have been a 1 by n plus 1 whole square plus a n plus 1 with a n plus 1 whole square less than 1 by n. The step prior to this one should have been a n plus 1 whole square common with a n plus, because I got a 1 and a n plus 1, so basically n plus 2 greater than 1 by n. This would have been my previous step. So n plus 2 divided by n plus 1 whole square less than 1 by n. And if this would have been my previous step, so probably this n would have been, no, the step prior to this should have a n with the n plus 2 being multiplied with the n plus 1 whole square less than 1. That means the step previous to or prior to this one would have been a n square plus a 2n less than equal to n plus 1 whole square. Or the previous step would have been a n square plus 2n less than equal to a n square plus a 2n plus a 1. So we should have started from this step, that n square plus 2n plus 1 is greater than equal to n square plus 2n, and from there we should have proceeded this way and finally would have come to this conclusion. So this is another way of solving the problem. So what I did is, this is what I am supposed to prove, and if this is what I was supposed to prove, so the statement prior to this or the step prior to this would have been like, 2 and 2 getting cancelled, so this statement. And then because I got a n plus 1, so probably the n plus 1 should have been in one side, so this should have been my previous step. And I got a squares here, probably I should have a square, should have some square here, so I put a square here with the n plus 1, so keeping everything look like same and this way. And then if this would have been the case, that step prior to this would have been just the normal addition, so I did the normal addition. And then when I did the normal addition, I found this, the upstairs is n plus 2 with the n plus 1 whole square and then 1 divided by n, and that means the step prior to this one should have been the n getting multiplied here. So the step n getting multiplied here, then this becomes a n square plus 2n, which is less than equal to n square plus 2n plus 1. So this is actually the step from where we should have started in order for us to get into this step. So it's not easy, like from where probably I need to take the step, because normal intuition does not say that I should start from this approach. So whenever you got no idea from where and how to start the problem, the best option would be to start from the end and try to get the solution. Next, let's do one more problem similar to this. Uh, 1 by 2 plus 2 by 2 squared plus 3 by 2 cube plus n by 2 to the power n is equal to 2 minus n plus 2 divided by 2 to the power n. This is a statement I need to prove using induction. So again, base case. So right hand side I put a 2 minus 1 plus 2 divided by 2 to the power 1. So 2 minus 2 plus 1 is 3 by 2. 3 by 2 is 1 and half. So 2 minus 1 and half is a half here. And here also I got a half. So this statement holds true for n equal to 1, base case. Now I assume that the statement will hold true for n equal to n, and then I will try to prove that the statement should hold true for n equal to n plus 1 as well. So this is till n. So up to n plus 1, it should be a half with a 2 by 2 square, a 3 by 2 cube, a 4 by 2 to the power 4, all the way to n by 2 to the power n plus a n plus 1 by 2 to the power n plus 1. That should be equal to 2, and the n getting replaced with n plus 1, this becomes n plus 1 plus 2, which is n plus 3, and 2 to the power n plus 1. So this is what I am supposed to prove. Well, if this is what I am supposed to prove, maybe what I need to do is take the right hand side. So, left hand side. So this is what I have in the left hand side. So we know from here to here is 2 minus n plus 2 divided by 2 to the power n. And then I am further adding up a n plus 1 with a 2n plus 1. Well, in doing so, now I can very easily take the LCM, which turns out to be 2 to the power n plus 1. And if that is the case, so this becomes 2 into 2 to the power n plus 1, and this one is 2 into n plus 2, and this becomes a n plus 1. So that means this whole thing actually is 2 to the power 2n is actually 2 to the power n plus 1 into 2 is actually 2 to the power 2 into 2 to the power, so 2, this is 2 into 2 to the power n into 2 minus 2 n plus 2 plus a n plus 1, and the whole thing divided by 2 to the power n plus 1. Well, this is 2 to the power n into 2 square. So 2 square into 2 square. So minus 2n plus 2 plus a n plus 1 divided by 2 to the power n plus 1. So this will be 2 to the power n plus 2, and this one is minus 2n plus, minus a 4 plus a n plus a 1 divided by 2 to the power n plus 1. So this becomes minus 2n plus a n, so minus 2n, so minus 2n minus 4 plus n plus 1. So minus 2n minus 2n plus n is minus n. So this whole thing, 2 to the power n plus 2 will be as it is, and this is minus 2n plus n, which is going to be minus of n, and then here I got a minus 4 and a plus 1, which is minus 3, and then the whole thing divided by 2 to the power n plus 1. So this is going to be 2 to the power, so maybe I need to rub this portion. So this is going to be 2 to the power n plus 2 minus say n plus 3, whole thing divided by 2 to the power n plus 1. Well, this is going to be 2 to the power n plus 2 with a 2 to the power n plus 1 minus say n plus 3 into 2 to the power n plus 1. So 2 to the power n plus 2 and n plus 1. So this is going to be a 2 minus a n plus 3 divided by 2 to the power n plus 1, and that's exactly what I am required to prove, QED. So what exactly I did, whatever I have, I kept it as it is. I took the left hand side and then I replaced this whole thing with this value plus the extra n plus 1 term I had. So I put that and then I did the normal arithmetic and I ended up getting what I am supposed to find. Okay, let's try to look into another problem, and the problem is given A1 being defined to be equal to 1, A2 is defined to be equal to 2, and the A3 is defined to be equal to 3, and then they have given a relation a to the power n is equal to a to the power n minus 1 plus a to the power n minus 2 plus a to the power n minus 3, and for all n greater than or equal to 4, we need to prove a to the power n is less than 2 to the power n. Now for n equal to 1, base case. So here I need to take 3 base case. A to the power 1, sorry, n equal to 1, so this becomes a1, which is less than 2 to the power 1. A1 we know is equal to 1, so this is true. What about a2? Less than 2 square. A2 I know is equal to 2, and 2 square is 4, and this also holds true. What about a3? A3 I know is equal to 3, and definitely 3 is less than 2 cube. So this also holds true. So the base case holds true. Now, so this is what I have for the base case, and then I need to prove these statements. So I already graphed what I require to prove. I need to prove a to the power n is less than 2 to the power n. Sorry, a n. This is what I am supposed to prove using this given fact. Okay. Now, since I'm assuming I already proved the base case, and then using induction hypothesis, I assume that this particular statement holds true. So a to the power n is less than 2 to the power n. This is true using induction hypothesis. So if this is true for n equal to n, what I need to prove for n equal to n plus 1? So what I need to prove, a to the power n plus 1 is less than 2 to the power n plus 1. So this is what I am required to prove, and this is what I have using induction hypothesis. I'm assuming this to be true. Now, the first thing is whether I can convert this into this. Well, possible, because the moment I am multiplying 2, so this becomes 2 to the power n plus 1. Well, now what is 2 into a to an? So this is an plus another an less than 2 to the power n plus 1. Well, I know what is an. An is an minus 1, an minus 2, and an minus 3. So maybe I need to replace this an with an minus 1 plus an minus 2 plus an minus 3 plus an less than 2. And now what is, we know an is this one. So what about an minus 1? Since an is this one, so an plus 1 should be an plus an minus 1 plus an minus 2. That should be the value of an plus 1. So here what I have is an minus 1, an minus 2, an minus 3, and an minus 1, an minus 2, an minus 1, n minus 2, and an. That this plus this should be equal to an plus 1. So I can replace this and this with an plus 1, and then the an minus 3 I am keeping it as it is. That should be less than 2 to the power n plus 1. And that's what if this is the case, if this number is less than 2 to the power n plus 1, and this number definitely is greater than a n plus 1, therefore a n plus 1 is less than 2 n plus 1. QED. Proved. So what I did, so here I am being given a condition that an is equal to a n minus 1 plus a n minus 2 plus a n minus 3, and again further few conditions are given that a n is equal to 1, a 2 is equal to 2, and a 3 is equal to 3, and I am required to prove a n is less than 2 to the power n. So I use the base case. In this particular question, I was required to take 3 base cases, because here I have got 3, a1, a2 and a3. So I took all the 3 base cases and I found them to be true. And then I assumed using induction hypothesis that this particular statement should hold true. And then I am required to prove that the statement should hold true for n equal to n plus 1. So I replace this n with n plus 1, and this is what I am required to prove. Being given the condition that an is equal to this value, so from this I managed to get the exact an plus 1 how it should be. So this is how the an plus 1 should be. So since I am required to prove this from this, the only way I can somehow get this from this is multiplying 2 both the side, because whenever I am multiplying 2 I would get a n 2 to the power n plus 1. So that's exactly I did multiply 2 both this side, and by doing so in the left hand side I got 2 an, and I split it up as an plus an, and I know that an is equal to this value, so I put that value of an and I keep 1 an as it is, and then using the fact that an plus 1 is equal to this, I change this value to an plus 1, and I did that, and by doing so I got that this whatever I have is greater than 2 to the power n plus 1, and this particular thing definitely is less than an plus 1, or in other words an plus 1 is less than 2 to the power n plus 1. Done.